Hello everyone, I'm pleased to introduce our work, Patch-based 3D natural scene generation from a single example. Our goal is, by only using a single exemplar, we can create a diverse set of scenes with photorealistic appearance and detailed geometry. 3D generative models aim to synthesize 3D contents with realistic geometric structures and virtual appearance. While precision models are capable of mass-producing particular 3D models, they take expertise and time to obtain rules and collect assets. A more relevant direction is the exemplar-based one, where one of few exemplars are provided. However, existing methods only can synthesize geometry and can handle simple things, such as terrains. Deep generative models are trained on large volumes of images of a specific category. They usually require a large number of training data and are limited in their ability to vary scene types. As for image generation, many works are focusing on learning generative models from a large amount of images. Some works attempt to learn a generative model from a single training image, but these learning-based models typically require a long training time. A classical patch-based approach that dates back long before the deep learning era, showing amazing performance without the need of training. We'll achieve our goal from the following two directions. First is to find a proper 3D representation, which should be explicit and can render photorealistic results. Then we should design an efficient and memory-friendly algorithm, which can handle different types of scenes. So we proposed a patch-based framework using a neural representation for 3D scenes. We use PlanVoxels as the base representation for example scenes, as it uses radiance field and volume rendering to render photorealistic images. Meanwhile, it uses explicit sparse voxel data structure, which is regular and easy to manipulate. However, natively use them is unsuitable. For example, density values are not well bounded, contain outliers, and cannot accurately describe the geometric structure. And spherical harmonics values are high-dimensional, so we perform feature transformation in advance. Then we use a different representation for synthesized scenes, which is represented by a mapping field that stores the coordinate in the exemplar space, instead of the real value that stores geometry and appearance features. Starting with the synthesized scene, we map the coordinate to the exemplar space and use volume rendering to render a novel scene. A key idea is to synthesize the mapping field S that can map the exemplar scene to a similar one. We first reshuffle the mapping field using Gaussian noise. Then we build a pyramid to gradually optimize the initial guess. During the optimization, we reassemble the patches from the exemplar to update noisy scenes, and the generated scenes contains only patches from the example and vice versa. We use an exact to approximate manner to reduce the computational requirements and memory usage. As a result, our framework can synthesize high-quality results. Let's see some results. From a single example on the left, our method can generate diverse samples with highly realistic geometric structures and virtual appearance. Please note how realistic the appearance of the generated cactus is, while also having rich geometric details. And also the mountains. Even with a complex structure like outdoors, none of existing 3D generative models can achieve these results. We show that our method is efficient to support generating scenes of different sizes of the exemplar, and particularly of a much higher resolution and different aspect ratio. The resolution of this scene is 1000 by 500 by 200, and will render a 4K image of the scene. Our method preserves details in example scenes, and we can render high-quality imagery created with generated scenes. This scene is obtained using Google Maps. A particular feature of our method is the photorealism and view-dependent effects of the exemplar are inherited in the results. See the reflection on the sea changing under spanning cameras. and also a very realistic law. We compare a method to Graph and Stelner, which are GAN-based 3D generative models, and GPN3D, which trivially extend 2D method. Generally, GAN-based baselines suffer from model collapse, producing almost identical results. GPN3D cannot synthesize high-resolution results due to computational efficiency issues, and quickly falls at coarse scales. For quantitative comparisons, ORS performs baselines by large margins, suggesting high quality and diversity from both 2D and 3D perspective. The versatilities of our method into several 3D modeling applications with our unified framework. We can retarget the scene to a different aspect ratio while maintaining the local patches in the examiner. Users can edit the input scenes, such as removal, duplication, and modification. For example, we can remove the mountain in the scene while inpainting the horse. By directly manipulating the mesh geometry, we can duplicate the instance in the scenes. Moreover, we can enlarge the mountain by changing the mesh. Given two scenes A and B, we create a scene with a patch distribution of A, but which is strictly aligned with B. As we use a heterogeneous representations for synthesis and example scenes, with the coordinate-based representation, we can redecorate the generated ones with ease, while simply remapping the examiners of different appearance. We test our method on images collected from real-world unbounded scenes. We only synthesize the region of interest and show promising results. In the future, we believe that combining classic computer graphic techniques with emerging neural representations can lead to promising directions and results. Thanks for your listening.